Hello, I'm Professor Norton at Worcester Polytech. I'm going to give you a little introduction to the video you're about to view. It involves a boot testing machine, and you're going to see two versions of such a machine. The first one you will see was developed at the Natick Army Laboratories in Natick, Massachusetts some years ago, and was used to do some testing of Army boots, which will be explained in the video. And the second one that you will see following that will be an alternate design that was done by some students here at WPI, starting out as a class project and ending up as several senior theses, if you will, over a period of a few years, still some time ago. But what you will see is a significantly simpler mechanism designed by the students to do what is essentially the same task of testing boots for boot manufacturer or the Army or whomever might be interested. So the first thing you will see is a visit to the Natick Army Labs. And let me give you some background as to how this whole project came about. I think it's kind of interesting. Back in the 90s, I happened to see a news broadcast on a Boston TV channel in which the TV crew had gone out to the Natick Army Labs, which is just outside of Boston, to do sort of a puff piece to show what goes on at that installation. And in the process of that video on the commercial channel, they showed this boot testing machine. And I thought it was kind of intriguing. For one thing, I thought that the mechanism that I saw on TV was rather complicated for the task at hand. And the other thing that I thought was it would make an awfully nice student project. So I contacted the folks at Natick Army Labs sometime after that, and a fellow named Bill Montori was very kind enough to let me come out to the lab and view the machine and talk to him and learn some more about it. And at some other time I brought a video cameraman from WPI along with me, and we made the video that you're about to see. So that was done at the Natick Army Labs. You'll see me a few years younger describing what it does and how it works. And then I'll be back to introduce the video that the students actually created of their design. We're at the Natick Army Research Labs in Natick, Mass, and we're looking at their boot testing machine, which is designed to test these combat boots for durability, particularly looking for the presence of leaks around the joint between the molded sole and the leather, or through the leather, as a result of the flexing that will occur when it's used. Now, in order to test that, there's this artificial foot. This is actually a prosthetic foot that would be used for an amputee, and it's been modified to put into it some electrical wires which provide circuits that will be shorted if the water, which has some saline added to it, in which the boot is going to be walking, if it gets through the boot, it will short this and you'll get a signal. So this boot, I happen to have a right foot and a left boot, or vice versa, but this will go into the boot, and the boot will then be placed on this machine. As you can see, it's at the moment sitting in the water box so that it could be filled with a saline solution, and that somewhat obscures the boot, but we'll remove the box in a moment so you can see better what is actually going on. The boot is clamped via this mandrel to a link on a fairly complicated mechanism, and I think if we turn it on, it'll be the easiest way to show you what that mechanism does. If we close the safety shield, the machine should start. The noise that you hear is the exhaust of air from the air cylinders. There are two air cylinders that are lifting that large carriage up and down to provide the heel strike motion. And a combination of links, which includes an epicyclic train, is providing a rotating motion to simulate the walking from the heel down to the flat foot to the toe-off position. I'm going to lift the safety shield now, and it will automatically stop because of the interlock switch. And now I'm going to cheat the system and push on the interlock switch with my finger, and so we can get a better look. But before I do that, I want to point out some of the features in the mechanism. Up here is the main drive shaft, and that is driving this gear, which is a sun gear of an epicyclic gear train. And behind this pivot, which is not very visible, is one planet gear, which is orbiting about that sun. And there's another planet gear here. That in turn is driving a crank linkage, which I'm pointing to right here. That crank linkage has a sliding joint with this long bar, and that bar is the one to which the shoe's mandrel is clamped. And not visible behind the water box at the bottom of this bar is a half joint, which is pretty well obscured. So it's a rather complicated linkage. In addition to those links and joints, there is a cam joint right here. You can see this linear cam. There's a shaped track in this block. And behind this link, not visible to you right at the moment, is a pin which rides in that slot. And you can see the grease in that slot, which has been provided for lubrication. Over here you can see the shaft of one of the two air cylinders, and that air cylinder, along with its mate, which is hidden behind the plate, lifts this whole plate up and down to give that heel strike motion. And that entire plate assembly, which is moving up and down, actually carries the motor, which is providing the rotation for that epicyclic train right here. So I'm going to now push the switch, keep my hands out of the way, and get a little better look, and you can zoom in on any of the features as it runs. Notice the epicyclic motion right there. And you can see the sliding joint. Normally this boot is run in a water environment. This is a splash shield, and this water box would be, as I said earlier, filled with some saline solution. And what I want to do now is remove that box, so why don't we just stop the camera for a moment and we'll take care of that. So you're putting a block under the heel to get the position correct, and moving the linkage around to the appropriate position. The shoe is now sitting more or less on the floor and on the 1-inch gauge block to get the right position of the mandrel. This is Bill Montori of the Natick Army Labs, who's in charge of this machine. He's putting it together for us right now. Okay, so it's all clamped back on. We don't have the water box. We remove the 1-inch block, and you can see that the boot is really not touching. I can get my fingers under there right now. And I'll take them out before I hit the switch and we'll start it running again. Now I want you to watch particularly the interface between the sole of the boot and the floor right at the ball, and notice the relative motion there. Watch the toe. Notice there's a scuffing motion as well as a rolling motion there. Get a little better look at the mechanism with that box gone. You can see the other air cylinder down here. There are two air cylinders parallel to one another that are supporting this plate right here. So this plate is guided up and down in linear motion. You can see this cam slot even better now. And again, the epicyclic train, you can see one of the gears right there. Motor, and in the back, if you can see it that far away, is some chain drive coming off the motor with a two-stage compound reduction up to the drive shaft. I think that pretty well shows what I want to show about this, Doug. So why don't we shut down for a moment. I also can adjust the speed on this, and Bill is going to turn it up to full tilt right now and see how fast it goes.
system here.
Okay.
Actually, we can see the epicyclic train.
We're rolling now.
Okay, why don't you... That's a good view of the epicyclic gear train. You can also see a pair of cams in the middle of that shaft, and those are being used to turn on and off the air cylinders. The cams are hitting what are called limit switches with those little lever arms with rollers on them. You can hear the sound of the air cylinder being synchronous with those cams tripping the switches. You can also see the chain drive pretty clearly here.
Well, now you've gotten some idea as to how the machine at Natick Army Labs worked and ran. And what you're going to see next is the result of two groups of students that had worked over 2 succeeding years on a design here at WPI originally for class credit, and then later, as I said before, as a student senior project. And they developed a linkage, a 4-bar linkage, to which they added a driver dyad, making it 6 bars total, and motor drive, and accomplished a very good approximation of the walking motion of a human. And as part of their project to prepare for that design task, I had them make actual measurements of both the kinematic gait and also the force between shoe and ground of a number of volunteers. I did that by contacting the colonel in charge of Army ROTC on campus at the time and told him what I was up to and asked if I could have some of his ROTC candidates come over to our engineering building in their battle dress, etc., and their combat boots, because we had a force plate in the basement of the building all set up to measure their force as they walked across, and we videotaped them. And his response was to ask, how many do you want and when do you want them? And they dutifully showed up on the appointed day, and the students, my students, made the videos and also measured the forces between the boots and the ground. These data were used then to simulate the motion kinematically and also to generate forces which were similar to the physiologic forces. And the mechanism that you will see the students will describe as having force transducers emplaced in it in certain locations, and you'll see some of the results of that. So back to the video, and you'll see a second design, which I think is a superior design to the first, student done and quite clever.
My name is Brian Zielinski, and this is a project for the Mechanical Engineering Department at Worcester Polytechnic Institute. My project partner is William Millett, and our advisor is Professor Robert Norton. The purpose of this device is to test fatigue wear on an Army-issued boot by simulating the walking motions of an average man. This linkage system here works out a coupler curve, which the boot follows in its path. The boot acts as the coupler point and walks through a motion which is similar to the walking motions of a person's foot. The linkage system itself is driven by a driver dyad, as seen here, which is connected to a motor which powers the linkage system at a speed approximately that of a fast stride of a person. The boot comes through and steps on this plate, as seen here, and goes through one complete walking over of the boot. In order to have the boot only walking in a forward motion and not in a backwards motion, as the boot comes through and hits the plate, an air cylinder which is hooked up to the plate down here pulls the plate mechanism down, so in the boot box back you will not have any contact with the plate. And then as it goes through the cycle, it starts to come back forward again. The air cylinder will go into a positive mode and push the plate mechanism up so as to have contact with the boot once again. Underneath the plate here we have two force transducers, one in the front and one in the back. The purpose of the force transducers is to measure the forces seen on the boot as it strikes the plate, walks through, and then toes off. And right now we can see a demonstration of the boot machine working. What I have here is a plot of the forces seen on the boot as taken by the force transducers, which we measured on the HP oscilloscope. As you can see here, the first curve here is the force transducer where the heel strikes the plate. It comes down, and at the peak is where the heel actually is pushing with its greatest force against the plate. Then as you move along toward the middle, you can see the meshing of the two curves, which is the front and rear force transducer, taking the measurements on the boot as the boot walks through the plate. As the boot moves forward, the transducer where the heel was begins to tail off, and then you can see that the peak, there's another peak here for the toe off of the boot, which is the front transducer. And then as the boot leaves the plate, forces tail off down there. For further information on the boot tester and a copy of the report, you can contact Professor Norton at Worcester Polytechnic Institute. Thank you.